Okay, first question. Compare the electric force holding the electron in orbit around the proton nucleus of the hydrogen atom with the gravitational force between the same electron and proton. What is the ratio of these forces? Okay, so the question wants us to compare the electric force and the gravitational force. Compare them how? This is provided for us by asking us to work out the ratio. So the ratio is the comparison between them. And in other words, it's what's the ratio, the one divided by the other. So the electric force, this is just Coulomb's law that we know, okay, times the absolute value of the charge on the electron times the absolute value of the charge on the proton over the distance between them squared. The gravitational force, and notice I put subscripts in this case to distinguish them from one another. This is the gravitational constant G times the mass of electron times mass of proton over R squared. Can I calculate these? Do I have everything that I need? Well, we've used these kind of terms a lot. What we don't know is what is the gravitational constant and what's the mass of an electron and a proton. This you can look up. An exam or test this will be provided. But in front of your textbook you can look up that the gravitational constant is 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. And the mass of an electron is 9.11 times 10 to the minus 31 kilograms, and the mass of a proton, much larger, 1.6726 times 10 to the minus 27 kilograms. Okay, so this is just from the front of the textbook, the values that we looked up. Now you can go ahead and calculate these two forces now, get values for them, and then divide those two values. That would be okay. But a smarter way to proceed is to first write down what it is that we actually want to try and calculate, and not to substitute any of the values, just to see if there might be any simplification, which often will be the case. So what happens if I divide these two values? Okay, so I take this one and I divide it by that one. In other words, I'm multiplying by the inverse of this one, in which the terms flip and the r squared is on the top and these three terms on the bottom, and then the top r squared will cancel with this r squared. So when you divide these two terms, what you're left with is k, absolute value of the charge on the electron, times absolute value of the charge on the proton, over g, me, and p. Okay, so no r squared term. So the radius has no effect on the answer in this question, and it's now simpler to calculate. Okay, so this kind of simplification, cancelling out of terms, will often happen. So I always try to write down what it is I'm trying to calculate first, before I go ahead and substitute the values, just in case I see it simplifies in a nice way. Okay, so let's substitute values. So what am I going to substitute for k? Well, normally I would substitute this for k. Or this is normally, I mean what we did most of the time. No, not kilogram squared, of course, Coulomb squared. Now, I'm not going to substitute this value in this case. Why not? Well, because the values that I looked up have more than two significant figures. This one has 3, this one 3, this one has 5 significant figures. So I'm not going to use the old k with just 2 significant figures. I'm going to use the more accurate one, 8.988 times 10 to the 9. So in keeping with the accuracy of the other values that I looked up, Newton meter squared per Coulomb squared. Is it going to have an effect on the answer? Well, I don't know. Probably not, but it's difficult to say beforehand. All I know is I looked up a bunch of values, and they have more than the 2 significant figures I normally use for k, so I'm going to use a more accurate value for k as well, in the hope that I'll get a more accurate answer. Though most of the cases it probably won't be more accurate, but we don't know. Okay, so what is absolute value of the charge of the electron? This is just 1.602 times 10 to the minus 19 coulombs. This is the absolute value of the charge on the electron. Absolute value of the charge on the proton is the same, so it is this squared. And let's see, I also use 1.602 instead of just 1.6 times 10 to the minus 19, for the same reason that I use this k instead of that one. Okay, divided by 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared, times mass of electron 9.11 times 10 to the minus 31 kilograms times 1.6726 times 10 to the 27 kilograms. Okay, now this is quite a big calculation. It is easy to make a mistake here, so I'm not going to go ahead and type times 10 to the 9, and etc. This is just begging to make a mistake. Instead, I'm just going to calculate these values and then I'll consider these times 10 to the power whatever terms afterwards. So I'm going to go ahead and say, right, this is 8.988 times 1.602 squared. That's what's going on above the line, divided by 6.67 times 9.11 times 1.6726, and that gives us that value. Okay, I'm going to write this in scientific notation, so not starting with a 2 instead of a 0. How many significant figures am I planning on giving in this answer? Well, this is just multiplying and dividing, so remembering the rule, I'm just looking at the value of the least number of significant figures. That would be this one. It's 3, so I'm only going to provide 3 significant figures in my answer. Okay, 2.27 in other words, times 10 to the minus 1. Okay, so that is what I just calculated. Now I'm going to consider all of these terms. Okay, so above the line I've got 10 to the power 9. So the power of 10 above the line is 9 plus, and then I've got 2 minus 19s, so it's just minus 19, minus 19. And then what do I have below the line? I'm dividing by 10 to the minus 11. That means I'm adding 11 to the power of 10. And likewise there I'm adding 31 and I'm adding 27 to get 40 times 10 to the 40. And so this is 2.27 times 10 to the 39. And that's it. In units, no units. I'm dividing just two forces, so it's newtons divided by newtons. It's just how many times the one force goes into the other force. So no units involved. So this answer tells me that the gravitational force magnitude-wise goes in this many times into the electric force, which just goes to show how incredibly weak the gravitational force is compared to electric force in this situation. And there, that is the final answer.